So, today's lecture we're going to talk about data structures and get into one particular type of data structure, a graph, because we're going to use that in the next few lectures, and we're going to talk about some of the ways that you represent that data. Now, I thought we'd go as an outline a little bit going over what we've the basics of graphs and the basics of data representation, and then get into some ways that we represent graphs in data structures, either in Java or in any language. So I just thought I'd go back over, because it's been a while and some of you have been on holiday, some of the basic concepts there about data. Someone's suggesting if I move to doing a stage, I could do 1,000. I'll look into that. Do that next week for the Discord. Okay, so hopefully you've done enough, dug back into your memory, and remember that there are some basic data types in Java, right? So these are data, right? They're not data structures really. They're just primitive data types, and they are ways that bits are represented, right? So these are very simple, a block of bits, and they're our way of representing them, right? And so bytes and shorts and ints and longs and floats and doubles and chars and booleans are all of those primitive types. Now, data structures we build on top of those. Now, interestingly, there's wrapped data structures, and technically string is not a primitive, it's a wrapped data structure. It's a wrapping of characters. However, because it's so fundamental and so low level, it's kind of considered a primitive almost. And if you can wrap an integer in an object that is an integer that contains the bytes. And that's because we want to add functionality to the raw data type, right? The raw data type doesn't have any functions associated, doesn't really know anything except it's a block of memory with ones and zeros in it, and the int tells us how to interpret that. Okay. And I'll just check everything's going right. Yep, that's good. Oh, that's what I should do. I should also start my Twitch streaming. The other Twitch people are going to be slightly behind. That's right. Okay, so once you've got these data types, we start looking at the standard collections. Now, I know in 103 you've looked at sets and things like hash sets and tree sets and sorted sets. These are collections of data. For lists, we have a linked list type and an array list. The array list is used a lot in Java, so lots of things use array lists because they're an efficient way of dealing with arrays, because you can expand them but they keep contiguous memory, which is quite useful. And maps and hash. So you have hash maps and tree maps and sorted maps, and these again refer to those data structures, right? So these are data types and data structures, but these don't cover everything. And when you build your own programs, you will want to have additional data structures that you create built on top of these. So when you did 103, I know that you did some graphs, and you did a graph structure with an adjacency list. So that's the first one we're going to look at today. You also did some binary trees and used some heap queues. You also did a lower South Island bus or lower North Island bus routes assignment, and you looked at mazes and how you represent a maze using arrays and using structures. So these are the stuff you'd done in 103. I'm hoping that is actually what you did in 103, and you still remember some of that. Maybe. So what we're going to look at is going to go beyond those. And one of the things I want to talk about, I'm really interested in where your knowledge is at around pointers and that fundamental understanding of what data is on the computer. So I'm going to mention it here, and then we're going to talk about it in labs and actually kind of dig in and make sure everybody understands that in the computer, there are just ones and zeros, just data. And we have, in C style languages, pointers to data. All that is an address of where that data is in memory. That's all it is. and you have linear blocks of data. So when you have an integer, what you mean when you go like int a, you're saying, hey, there's a piece of memory somewhere, right? I want you to give me a pointer to that piece of memory, and I want you to tell the operating system that piece of memory is mine. And when I use the word int, what that means is when you look at the ones and zeros in that block of memory, it's going to be interpreted as an integer, right? That's all it means, okay? So all of these data structures are just put on top of those basic pointers and blocks of memory, right? So everything going on here is just clever ways of seeing that. Okay, so objects are just a clever way of arranging pointers and memory to try and associate the data together into a single object, and also to associate code blocks with data blocks. Okay. So, as I talked about on Tuesday, we're going to talk about graphs, and it seems that I'm about to have my son hit my camera, which will be, or the sun hit my camera. Let's see, I'm going to have to put something up there to stop that soon. Oh dear. Oh well, we'll see how badly that affects the camera. I might have to shift myself around a little bit to prevent the camera from getting too in the sun. Right, so what I'm going to look at is that we have the nodes and edges. This is the way we define a graph, and we have the connections between nodes as those directed edges. There's also an additional word that I didn't use last on Tuesday, which is a degree, which is the number of edges that enter a node or exit a node, right? So you have nodes with edges connecting them, and the degree is the number of edges. We also have multigraphs, which gives us loops and complex graphs. So that would be undirected loops. We have our directed edges and a loop that comes back to the original node. Okay, so when we look at a data structure, when we talk about what's a good data structure and what's a bad data structure, and there you are, you're seeing, that's what I have to do. Let's put a sun shield up next to the camera, and hopefully that will be able to prevent me. No, that's too heavy. I'm fading out, which is a terrible thing to do for you while I'm giving you a lecture, and I have to do that. Maybe. Can I get this to do the right thing? There we go. Haha, got it. It was artistic lens flare. So when we talk about a good data structure, we have to understand a bunch of things about a data structure, right? Both how much space it uses and how much time it takes for us to access the information in that data structure. So when we look at a graph, we are talking about what are the common operations that you would find in a graph data structure. So, interacting with all the nodes in the graph, find all the outgoing nodes, the incoming nodes, interact with all your neighbors, and work out whether two nodes are connected or not, and also find the edges between two nodes. These are common operations. So there are kind of three traditional structures. I know last year they talked about two. I'm going to talk about three, partly because of the way that you had been introduced to the graphs data structures in 103 was by a node adjacency list, right? So you had a list of nodes, right? So it could be a list or an array list of nodes. From the list of nodes, you had a list of outgoing neighbors, right? So what that means is for every node, it contained a list, and that list contained the nodes that it was connected to. Okay, so you can imagine I have each of these nodes, and each node has a list of its neighbors. Right? So I've stored that in the nodes themselves rather than in in another data structure, right? So that's kind of a node adjacency list. So it's an adjacency list that's in each node. So if I had that structure, I would have this kind of overall structure of a graph. What I'm showing here is the actual structure of that graph. I haven't put the locations of those nodes. This is kind of a graph that is generated from that, or would generate that sequence of connections. So if we look at the time complexity of that graph system, of that node structure, then we can go through and say, well, how long does it take overall to access different parts of the graph when it's structured in this way? Now, if we're looking at kind of finding all the nodes, finding all the edges, I'm going to ask. Oh, just before I do, just so that we can keep up to date, I do actually have all of the code for these data structures that I'm using put into the repository in GitLab, which hopefully I'll just put it into the chat window in Discord and the chat window in Zoom. So if you want to go and have a look at some of this code, if you're thinking the code doesn't look easy to read on the screen, go and have a look in the code in there. This has some graphs and nodes and edges. So, and the graph is got actually, if I've got to get the right, if I go to the master, hopefully I sent you the right one. If we look at so if you go to master branch rather than the Windows branch, if you look at master branch, you'll find that there's an action event Java, but there are also, the graph will have multiple data structures in it, right? So go to that, have a look. So I need people to make some comments to me. If I hit enter on that one. What do we think finding all nodes would be when you have a list of nodes? How long will it take to find all nodes? Any thoughts? You've done your auto notation. Remember auto notation from last year? I'm looking down at the comments because your comments on that side of the screen, my slides are there. Order in, order in, order in. People are voting hard out for order in. And if you're in the lecture chat, you should be able to also vote on the lecture chat text channel, order in. Yes, you are correct. It is order in is the correct value for that. Now, if we go through each of these, to find all the edges, you have to go through all of the nodes and all of the edges. And so when you look at the thing above, we say n is less than m, and m is all of the edges. And because we have a list, we can just go through each node, grabbing the list of edges. So it's going to be basically the equivalent of going through all edges. So if we actually look at this, finding all nodes is order n because we have to enumerate all the nodes. Going through or enumerating or searching through, interacting with every one of those. If we have a look at the enumerating, the finding all the edges, we say it kind of n plus m, but because m is... oh, sorry, that's the wrong way around. I mean, this should actually, this should be saying, and I'll edit it now. I did that wrong. That is my mistake in typing. I wouldn't want to confuse people. We've said above that n is less than m. Okay. And go back to present. Sorry about that. n is less than m, but because m is bigger and it's an addition, for order notation we just use the kind of bigger number, so that would be go through all the edges. When we're finding edges in the node, in the graph, we have to go through the list of nodes and find the outgoing edges, but because that's on average, that would be what we call the degree. On average, that would be the total number of edges divided by the number of nodes. So here you can see we've got about an average degree of about 3 and a bit, right? Because it's each node has a degree of about 3, but there's a couple of 4s and a 5 and 2 6s, so it'll be a wee bit over 3. That would mean that our average order would be m over n, so it would be about 3, the number of edges by the number of nodes. Whereas our max could be a terrible graph where every edge is connected to a single node, and that's it. And so to find all the edges, you'd have to go through all the edges, right? Or to find all the outgoing edges, you'd have to go through all the edges because one of the nodes had all of the outgoing edges. That's not common in graphs. That'd be a silly graph. But when you're talking order notation, that's the worst case scenario. So we can talk about the average a wee bit. Find out the incoming order n, order m, because to find the incoming to a node, you have to go through every other node to find all of its outgoing vectors. And having gone through all those outgoing vectors, going, right, I'm going to sum all the times I appear in your list, right? So to find the ones coming in is really slow in this because you've only got the outgoing. If you want to interact with all the nodes, you're going to have to, again, we're talking about the max degree, so m over n. So you go to a node, have a look at all the nodes that are connected to it, go and find those nodes and interact with those nodes. Now, I put a double star next to the O notation there because this is where O notation falls over. And part of the reason why we need to, and we will, look beyond just O notation for understanding what's important about your data representation. Because if you splay your data all over your memory, then the idea of jumping around and grabbing random bits of data from random places in the operating system is incredibly slow compared to a block of data that you copied in a single on a single call. So although it's order m, and n over m, the fact that it's jumping around memory means that it's probably going to be terrible, right? So I want you to start thinking, okay, that's the order notation, but what does that mean in real life, right? And that's when jumping around memory becomes the big deal. For interacting with the incoming nodes, you're going to always have to search through all of the edges to find all the incomings, and so that's going to take a while. And the incomings will not only have to go through them all, but also have to interact and jump around memory terribly. So if you wanted to check if there is an edge between two nodes, basically you go to node 1 and see if it's got an outgoing, and that would be the outgoing, and you go to node 2 and see if it's got outgoing, and that would be the way you do that. So it's kind of 2 over the average, so kind of, again, the average degree. Okay. So time complexity for node analysis. So this kind of array, which is what you set up, can I get a comment from the audience? Is that consistent with what you did in 103? Do you remember doing that in 103 with like having a node and having a list of nodes it's connected to? Yep, good, great, okay. We're slowly getting back into it. For some of you, you did it over summer, so it's like a week ago you were doing this yet. But for some of you, it was back before summer when the world was different. So, so edges are the connections between nodes. Okay, so nodes are where is it? There. The nodes are the letters. The edges are, so the list of nodes there represent edges between A and B, and the edge is the line and the node is the square. Right, okay? So edges of the line, nodes of the square. So this is a way of representing those relationships. So this was okay for outgoing edges because they're connected and you've got a list of them in the node. Not great for the incoming edges, right? So you can improve, now one of the things, and one of the things you can do to improve for incoming is you trade memory for speed by creating both a list of outgoing edges, i.e. the nodes that you're connected to out, and the nodes you're connected to coming in. Now that doubles your storage capacity, right? Because you're now storing them both going out and coming in. that seems like a waste. And the answer is, well, yes, it is a waste. Technically, you don't need to do that. And it introduces the issue of, if I delete an incoming, right? So if I've got a list of incomings and I delete that one, and you still have your outgoing on your list, suddenly I've got a clash. I've got a disagreement, right? Because my information is now different to your information, right? And that's the bad thing in a data structure. So one of the things you have to watch out is how, if you build in redundancies, how you keep your cached redundancy up to date. This becomes a big issue in databases, and I'm sure you'll talk a lot about dirty flags, and when you go into databases, it's all about sort of how do you keep these caches up to date. But when we look at storing more data, sometimes what we're doing is we're trading off memory for speed. Right? So we pre-calculate things, store them, and then use that additional memory to mean we don't need to do those calculations a second time. So you could keep two lists. You could keep all the lists going out and all the nodes coming in, and just in code ensure that if anybody wants to delete something, it has to delete the pair. It has to find the other node and delete the associated adjacency list. Okay, so you have an outgoing list and an incoming list, so out neighbors and in neighbors. And you can find a node by going through and actually saying, okay, I've got out nodes and I've got in nodes. How do I get those? Well, the I here is the position in the list, right? Because you don't care about the label of it. You're just going through and finding its position. You could do a for each and step through it. If you're using a hash map or other data representation, you could find it by its key, but we'll stick with position in the list. Okay. Now, when we're talking about the time complexity, the worst case for finding neighbors is order n, because if the graph is fully connected. So this is kind of going in, well, what more can we think about here, right? In practice, complexity is much smaller than if you have a fully connected graph, and that's why we get at that degree, and sometimes they'll call degree of node. You'll see as some mathematical phrase, which is the number of outgoing and combined with incoming. The maximum degree of a graph is the big delta. So wouldn't having an outgoing and incoming be the same as having unidirectional nodes? No, what I'm saying here is if you have outgoing and incoming, you can have single directional nodes, right? So I have all of my edges going out, but my edges coming in are not my edges. I can't go out by my incoming, right? So if you have a directed node from A to B and I have from B to C, B would record that A has got an incoming and C has got an outgoing. Okay, so that's why I'd need two lists. I wouldn't just have I'm connected to these people. I would have I've got a directed edge from that person to me. And so I'd have two lists, one of all the ones that are going out and one of all the ones coming in. So in this model, the list was just storing the nodes. Yes, so this is, if you're talking directed nodes, you're talking one-way streets. And so you have what's coming in and going out. If you only know the things going out, you can reconstruct the ones coming into you by looking at every possibility around the entire network of who might be sending you data. So that's the challenge here. When we look at a degree of a graph and the degree of nodes, and this is kind of graph theory stuff we'll be talking about, and we'll talk about degrees. An intersection is usually 2, 3, 4, sometimes up to 5 streets all arriving at a point. And as the comments have been coming in, normally we think of these as 2-directional streets, but if we're talking about edges, directed edges, they would all be kind of one-way streets coming in and one-way streets going out. You could kind of think of an intersection as having a bunch of one-way, like 2 sets of one-way streets coming in and calling them different roads when you have an intersection and stuff. But that idea of generally, if you have streets coming into an intersection, you have these edges coming in. And if you think of it about a city, the number of intersections, n, is huge. but the number of edges is not very large because the degree is limited. How many connections you can have in any single node is limited. When we talk about three-dimensional shapes and we use tessellation and triangles on a three-dimensional shape, each vertex has a limited number of points, of edges that come to a vertex. Right? And so if you look at a triangle mesh, there is a limit, if it's a straight mesh, to the degree of any particular vertice. Right? So you'll see degree quite a lot in graphics as well as in graph theory. And if we look at the complexity of finding all the incoming outgoings, when the maximum degree is much less than n, which is most graphs and most networks, then the cost of going through the neighbours is generally quite small because the number of neighbours you have is very small compared to the number of total nodes there are. Okay, so understanding the type of graph you have is very important to understanding what matters in terms of the relative cost of doing things. Okay. So another way of representing things, which is now a horrendous way of representing a graph, and I only put it in here partly just to show how bad it is if you put a list of nodes, so you've got your list of nodes completely separate, and then separately from that you have a list of edges. Right, so this is all of the individual edges are just put into a list, and each edge knows its start node, its end node, and it has a weight. So now we're going directed and weighted graphs. This is great in terms of flexibility, but it's really bad when you take this network of there's a line from A to B and a line from A to H and a line from A to I, and there's a line, and this is also showing a bidirectional, that's why I've got all the edges, but you get this massive long list of all of the edges. So to do anything, it's going to be slow, right? Because you've not got a data structure that helps you organize any of these things. So so what do we think of finding all nodes? Well, that's going to be simple. We've still got order n. Finding all edges, well, that's order m, so that's still fine. Finding all incoming edges of a node. How would you do that? Thoughts? Check the middle column. Yep. But to do that, you're going to have to go through every single edge, right? Because that's really slow. So that's going to be M, right? That's going to be the edges. Every edge you're going to have to go through and check, do you end up going out of a particular node? So for the outgoing, you would check the first column. For the incoming, you'd check the second column, right? So outgoing, I'm in the first column. Incoming, I'm in the second column. Now, at the moment, these are sorted, but they don't need to be sorted. I'm sorry, William, I'm in a lecture. You can't talk to me. That's my son. Sorry, he just wanted go and talk to your mother. Sorry, it's lecturing from home. That's what we get. So you're going to have to go through that whole list, and that's really slow. So in this case, I put a third column in there, which are all currently ones. That's because we could have different weighted edges, right? So if we're trying to minimize everything, we could just have a list of A and B, but if we're going to have weighted edges, we'd have A, B, and a number. At the moment, those numbers are all 1. You could also, rather than actually have the nodes themselves, you could have an index indicator. You could have an I, which would be the number of the position of the node rather than the actual node itself, right? Because there are lots of ways of indirectly referring to something, right? So I could refer to the node by its string name. I could refer to the node by its position in the list of nodes, or I could refer to the node as the actual object that is the node, right? So these are 3 different ways of referring to things. Referring to the node itself is direct. The others are indirect, and I have to have some way of finding the node from my indirect reference. So if I only know your position in the list, then I have to go to the list, find that position, and then extract you. If I only know the string name you have, I have to go to the list, find the string, and extract you. If I've got a directed pointer to you, I go, that's where your memory is. That's what I mean by a pointer. I can point directly at you and go, you're in that location. I'll go there and find you. Okay, so there are lots of different ways in which you would store this information. So if we have a look through, this is terrible because almost all of these operations, all of these N and M's, are in fact having to go through every node in the list, in the edges array, to find any of this information. Right? If you want to interact with the outgoings, you have to go down and find all the outgoings. If you want to interact with income, you have to go down and find all the income. So all of that is slow. Right? And if you want to check, is there any link between two, then you have to go through and find them all. Now, if you created indexing and you created hash maps, you created other ways of representing this, you could represent them in different ways. But if you just have it as a straight array list, it's going to be really very slow. Okay, so this is what we're saying, is that, this way of storing it is not efficient for pretty much doing, my reveals have got a bit out of sequence. So finding this information is not efficient for finding outgoing, it's not efficient for finding incoming, because you just have to basically go through the entire list saying, hey, are you equal to this? If they get the to and they get the from, and then ask, hey, are you equal to this node that I'm looking for, and then add that to a result list, right? So you can do it, and it means the information's only stored in one place, and you know where all the edges are, but it's really slow because you have to regenerate all the connections by these indirect lookups, right? And by searching through it all. So order M, terribly slow. It's not a good way of doing it, right? Just storing those edges completely independently, it means you've got a lot of indirect lookup. So one of the other ways is to say, well, can we build a matrix connection so that this has very fast lookup? Okay, so what you're trying to do is find what is, in this case, the weight between two edges. This currently is symmetric, but it wouldn't have to be. This allows you to have very, very fast lookup of the weight between any two nodes, because this data structure of a matrix is now indexed by the node. So you can look up the node and immediately find the connection between that node and another node. So it's got an order 1 lookup on, is there a connection? Very fast. It's a little bit slower on other things. It doesn't deal with multi-graphs. So this is a problem with graphs where you have more than one connection between two locations. This doesn't deal well with that because there's only a single item in in this array, which is the weight. And when there's nothing there, or an infinite score, you have no connection. When there's a number, that is the connection between these 2 points in the graph. So this is an adjacency matrix. We can have a slightly different version, which is the bitwise adjacency matrix, where they try and save even more space by saying, well, rather than just having the numbers here, how about we have the just a binary representation, so bits that represent whether or not something's connected or not. And so now this is very fast and very small for looking up the truth or false of connections. If you're heavily connected, this is a useful representation. If you're not heavily connected, then this becomes a very, very sparse matrix, which is bad for storage, and potentially, as it gets very large, moving it around memory can be bad for speed as well. So that style can't even have weighted edges. Okay, but if we look at how we actually interact with this, and as I said, there's a link to code where I implemented all of these bits of code. Here's a two-dimensional list, two-dimensional matrix, and I've set it up as an array list of integers, right? Where I've actually now, instead of just having a number here, what I did is said, well, if we wanted to have a multigraph, I could have lists in each of these squares. So instead of just having one or having a number, I could have a list. Now, this is a matrix of an array list of integers. So this has a two-dimensional array, right? So an array, and inside that array there is a list of integers. Now that actually means that technically there is a set-sized array. Each of those array points holds a pointer that points me at a piece of memory that is an array list that can expand by adding more items into it. So it's a level of indirection, and it's going to take up more space. Within that, I can go through and cycle through the nodes and through the both the I and j, find all the outgoing, and kind of build that adjacency list by adding a number to the adjacency list, and then otherwise leaving it null if there's no connections. And if I wanted to add more connections, I would add them to the ij, saying, oh, I've got another ij connection, and I'm going to add this number to that connection. Okay? So that would be a deeper data structure, which is got the additional it's an agency matrix with a multi-graph approach, which has a list underneath the array. Okay, so we're kind of building up quite complex data structures here. For the complexity analysis, I won't go into that complexity analysis with the arrays. I'll just go back to this matrix because it's a wee bit simpler. But the simple array here is a two-dimensional matrix with an integer weight, which stores quite small, so you can move it around very easily. But if we look at the outgoing, if we look at each of these, we look at the finding the incoming nodes. So finding all the nodes, we're happy that that's an n. Finding all the edges. What would finding all the edges be? Who's going to shout out an answer into the text? Finding all the edges when you're given this data representation. Order n squared. Well done, that man. Or woman, or whoever you are. So, yes, it's order n squared, right? And that is really quite slow. So here, look at that. That's the big one, order n squared, finding all the edges. Unfortunately, and all of these operations now are order n. Now that's given that we know that n is much smaller than m, right? Because m is all the edges. Now it's just the length of the node. So it's generally faster than. So is n squared greater than m? That depends on your m. Generally, n squared will be larger than m. Okay, so m, well, technically, unless you've got a multigraph, right? In a non-multigraph, which is this is no multigraph, m has to be less than n squared because n squared would be every node connected to every other node. Okay, so m has to be less than n squared in a non-multigraph, not fully connected graph. If you've got potential multiple edges per node, then your m could get larger than n squared. But n squared generally is going to be much larger than m. And so if you really were trying to do something where you wanted to find every edge, this would be a bad representation. However, that's not necessarily the option you're actually interested in, right? So you might be interested in, for the roading network, how do I get from my house to the university? Very rarely are you going to want to have a look at every piece of road in the entire Wellington network, right? So finding all edges might not be something you do very often. Finding short routes might be something you do all the time. So understanding when you're going to do that means that whether you need to be afraid of that n squared or not. So finding all edges is n, finding incoming nodes is n, directed the incoming outgoing and interacting with the incoming outgoing nodes. You're going to find a node and go straight to it, so that's not too bad. And check if two nodes are connected. You have an instantaneous order 1 because you can just do that data lookup into the graph and go into the matrix and go bang, if there's a number there, we're connected, right? So that's going to be very fast. So if you want to know if two things are connected, this is great. If you want to find every edge, it's terrible. So that time complexity, and if we look at the comparison between these, when we looked at the adjacency matrix, so without the multi-graph component, it's order n for a lot of these and n squared for some of them. And if we look at the adjacency, when you have the nodes, each node knowing who it's connected to, then you've got order n, you've got m is smaller than n squared generally, as was the question. But the degree on most of these operations, and at the bottom, the order degree. So if you do the check if two edges are connected, if that's what you do almost all the time, then your adjacency matrix is a better option. However, if you're stepping through all of something, then you might find the node adjacency as being better than the adjacency matrix. Right? So you have to understand which operations you're doing the most of. So if you're doing a mix of these, then maybe doing node adjacency is going to be better. If you're doing that last specific one of checking, then you want to use the matrix. So I've got 7 minutes left, and I'll get through my summary, and then we'll talk a little bit about the assignment, and I'll talk a little bit about code and how we're going to be running code in the course, or in my part of the course. So the adjacency matrix is a way of doing a two-dimensional matrix, and you saw the double square brackets. We can get into like how that represents if you're interested in the detail of the representation there. But this idea of starting to think about how two different data structures have different efficiencies when we talk about their storage and also their typical usage. One of the things I want to start you thinking about is the trade-off between space and speed. If you look at trying to optimize things, often it's around this idea of how do I make things small enough so I can move them around efficiently inside the computer and have all the things I need move together when I want to do the calculation. So for example, if you actually want to make something fast, you need to get all the memory contiguous, because then it can all come in to the CPU and be handled all in one block. Right? If your data structure is pointers and jumping all over memory, then every time you want to interact with something, you have to wait for it to come out of RAM. And that takes thousands and potentially tens of thousands of operations on the CPU to get one thing out of RAM. And so what you want to do is you don't want to do that. You want to get it all in one go and process it. So although I'm starting with the O notation, and the O notation is what other lecturers will talk to you about in terms of understanding structure, I also want to start looking and digging into that memory representation and the order of the size of memory being allocated. Now, unfortunately, Java has a garbage collector and handles most of the memory for you, so you don't often get to play directly with the memory in Java, but you can certainly see some of the general scope of how big a data set is when you start putting it into the normal data items. So the adjacency matrix, if you're checking links between them, is great. The node list, if you're needing to point to other things, is the way to do it. In my sample answer for assignment 1, I actually use a bunch of hash maps because they're relatively quick for some things. And so if you know you've got a string and you need to look up a set item, a hash map is a pretty fast way of doing a bunch of that. You did look at hash maps in 103, so that's a reminder that those are a good cornerstone of building other data structures on top of, right? So you can use hash maps as a way of storing something that you then build a data map on top of. So, do I have any questions as to that? When is the assignment 1? So, assignment 1 is due in 3 weeks' time, and at the moment it is going to be put up, and I have it here, and I'm just finishing it off in terms of getting the write-up complete, and making sure that I've got all my sample code structured down, because I don't want you to write the whole thing from scratch. So we're giving you template code. I've finished writing the solution, so I now have to strip out the bits of the solution that I want you to come up with. What we're going to do is, and if I go to my OBS and we jump into, I have to look around the corner to get to my OBS. So if I go to that one, that's my, where also I use Overleaf for my LaTeX writing. But if I grab the assignment sheet, actually I can also grab the graph viewer. So this is currently how my assignment is working. This, and I've done the basic rather than the advanced. So if I zoom out, at the moment you can probably start to recognize that as looking vaguely like Wellington. That looks vaguely like Wellington. You can recognize something, sort of the city and the hut. And if I zoom in, zoom out, zoom in, I can move it around, and I can click on areas, and it will tell me what part of the city I'm looking at in terms of the bus network and what's connected. Okay, so that's some of the core functionality I want you to get to. And at the moment I'm just searching on the number, but I would like to see, so those are all of the stops that start with the stop number 716. What I want for the try storage is that you can search by name. Okay, so I'm nearly there. Okay, in terms of the workload, we are looking at similar workloads to, well, more than 103. It's a 10% assignment, and it will be due on the 23rd, I think it is. I'll actually just confirm that. In there, where is it due? Assignments. Yes, due the 23rd. So it's due the Wednesday night. It's 23rd. So it's the 3rd today. So it's 20 days. So nearly 3 weeks. I'll finish off releasing that tonight. So we have that full 3 weeks. We'll be going over JavaFX. So this is using JavaFX and an FXML. I have JavaFX in the lab, in the lecture code that I've got out there. And tomorrow at 12 we will be going through setting up JavaFX, having a look at how JavaFX represent things, and discussing some of how you can show things on a graph on screen, and not using the ECS 100 AWS or Swing stuff. We've moved to JavaFX, and also I'm using Visual Studio Code, so we'll also help students tomorrow start setting it up, so that on Monday morning, when the tutorials start, you'll be able to start implementing and playing with data structures and having the help from the tutor to make sure that everybody has access and is able to use the code. Are the tutorials compulsory? No, the tutorials are not compulsory, except that you have to go and have the in-person tests in the tutorials. And if you don't follow what's going on and don't go to tutorials, then you'll probably fail. So that, yes, you'll get all of the bus data network. So I actually had this, we've got all of that there. So the bus data network comes from Netlink, and I downloaded that, and if we go here, I've got, this is the assignment that I've written. I'm just cleaning up. So I actually do have in here this link, which is the opendata.metlink.org.nz. I downloaded all of the Metlink data as it was on the beginning of this month, and I haven't cleaned it up, I haven't altered it, I've just read the data as they share it from that link. So, and I'll give you all of the data because they give you a lot more data than just the stops and the edges. They also give you trip information about accessibility and bicycles access. They give you the names of the operators. They give you the timetabling information. And if you're really clever, you would be able to actually set up the API connection to Metlink and be able to extract the real-time bus data because it's the same API. Right, so this is the straight Metlink API. Okay, so I need to stop because it's already past 6 o'clock and some of you need to get away. So do I have any last questions? That will be up tonight. I'm sorry I didn't get it out before, like immediately before the lecture, but I was just making sure that I'm going to get it all correct and that I've done it all correctly. Okay. So do I have any questions? I've got behind on my Zoom, so my Zoom is being challenging. So stops, stop pattern, trip data. That's what's going up. Shortly after the lecture, I'll just finish writing it and I'll finish the spell check at the end, and then put it up. Do you have any other questions? What VR headsets do I use? So technically, I have my Vive Pro up there for when I want to do high res stuff, and for interacting with people. I currently have. Where is it? Oh, there it is. I have the Flow, the HTC Flow, HTC Vive Flow. So that's a kind of lightweight one. The nice thing about this is you can wear it and actually see underneath it, so you can actually be wearing it and do coding while you then look up at the VR world and then back at your coding. So there's some usefulness there. Any other questions about data structures? And is the maximum number of outgoing edges for a node always the same as the maximum number of incoming nodes? Absolutely not. The maximum outgoing is often different to the maximum incoming. When you look at flows merging, so you could have like 3 incoming and 1 outgoing, would be a merge of 3 into 1. Merge of 2 into 1, that's quite common. So no, the degree in and degree out are usually different, particularly if you've got valves in a flow system. Any other questions before I stop the recording? No. Okay. So if you also the last one is I sent that link. Did any of you have a look at the code link that I sent? This is if I make it bigger. So this is some of the code that I have in that. So this is the Comp261 Lecture 2. And I have a list, an array list of nodes, and this is a double weight matrix. So this would be the adjacency matrix. And here, this is a array list of adjacency matrix. So that's for the matrix for multigraph. So you can go and have a look at the code there and download it and run it and play with it. And we'll have a look at making sure you can run that tomorrow and you understand how that graph, that code is working. Okay, so I will just talk a little bit more about incoming and outgoing edges, and I'm thinking I should probably, and I'll have to do this for next week, set up my whiteboard or my Wacom tablet so I can actually do the drawing on my tablet. Okay, so The best example of this might be if you think of a river, right? So you've got a river where two parts of the river come together. You could think of that as a node, and then the rest of the river would flow out. Now, a river has a very directed flow. It flows from the mountains down to the sea, and so that would all be a directed graph. And so if you were standing at a fork in the river, you'd have two incoming and the one outgoing as it goes out from this juncture point. Okay, so that would be directed. If you think of a tree is a classic directed graph. It has a direction where the sap flows up through the tree and out to the leaves. So when you look at the trunk, you've got all of them, and you get to where a branch comes off. Right? If you think of that as being a node, you have a line coming up to it, and then you have a branch going off one side, and another line, and that line goes up. Right? So it has an intersection, and it has two outgoing edges and one incoming edge. Okay? And the degree would be the number of branching that you can have at any node. So if you look at some trees, there are some trees where the leaves are bifurcated leaves, and so they can only come out in pairs. So it's got a maximum degree on a leaf of 2. And so you can kind of look at it, whereas you can have some that will divide up into 3, right? Or some that will only ever divide into 2 at each point. Okay. We will have to sort out Java. No, tomorrow I'm sorting out JavaFX for you. That's what we're doing. We're sorting out JavaFX. If you're in the lab, JavaFX is already installed in the lab, and if you have a look at my code here, I have in the code a branch which is the Linux branch. I need to fast forward it so it's got all the data on it. But in the Linux branch, you have the if I go to the source, I go one up. Source, you'll see that. Oh no, I need to go code. So if we go all the way back to the Lecture 2 code in the Linux branch, we have the VS Code file here, and it has the settings which point the system to the right jar files, which are in user packaging Java, JavaFX, SDK11 on the Linux systems. And if we go back, and I know the lecture's over, but people want to leave. We'll be covering this tomorrow as well, so this won't be the only time you see it. So we have the settings, and also, sorry, I meant to go to the launch. The launch has the setup for the module path setup for the Linux lab. Whereas if you are in Windows branch, and you go to the Windows branch, I have that set up to where my path to FX is. So I set up a path to FX, which is in my case is a Java SDK under C files Java/JavaFX SDK. So that's where mine is, and I use that path. But if you are also looking at VS Code and looking at the settings, it has my location for where I put JavaFX. When you download and install JavaFX, you have to know where it is, and then you would replace that with where you've put your JavaFX. Okay, so but we're going through that tomorrow, so that by Monday you'll have it all sorted. Okay. So, quick question around if there's an undirected graph from node A to node B, does that mean the degree of A is 2? No, that means the degree of A is 1. Right? So if you've got one outgoing node, you've got 1. If there's a outgoing node from A to B and an outgoing node from A to C, A has the degree of 2, B has a degree of 1, C has a degree of 1 because they've each got one node interacting with them, and A has 2 edges coming out of it, and so the the delta, the big delta, the maximum degree of the graph is 2, because that's the node with the maximum number of edges coming off it, would be A, which had 2, because B had 1 and C had 1. No, so the lecture slot at 12 till 1 tomorrow is going to be a tutorial from me, just going over Visual Studio and Visual Studio Code and VS Code and JavaFX, and going through some of the code that I've written and doing some live coding and talking about the code itself and helping you get set up so that on Monday morning when the tutes start, you'll actually hopefully have systems that work. So it's just the lecture slot is a tutorial tomorrow from me for everyone setting up their Java. If you take that information and get yourself set up for Monday morning, that's fine. Otherwise, the tutor will be able to help you on from Monday in the normal tutorial slot, getting things set up. Yes, the session tomorrow will also be recorded. How do you calculate the weight? Oh, the weights were just randomly assigned. There was no calculation of those weights. Those were weights that were just, it could be the length of the road. It could be how long it takes you to get down that path. It could be geographical location, or it could be challenge. So, if you have to go through dense bush, you might make that weight 10. Whereas if you've got a road, you might make the weight 1. So that wasn't a calculated weight. That was just if there happens to be an assessment of the cost of going from one node to another node. Okay. Oh, well, if that's all good, I will stop the recording now, and we'll see you tomorrow, when hopefully I won't have to worry about the sun, because it won't be shining in through my window. Have a lovely Thursday night. I will go back to finish writing up the assignment, and so it will be being updated. You can watch me update it tonight. Okay. Have a great evening, and we'll see you tomorrow. I need to actually get to the right screen to stop recording. Okay, so stop streaming. Stop.